All right, we just spent a fair bit of time there on Cartesian geometry. But the other type of geometry we do, of course, is Euclidean geometry. And there very much is a relation in both. And you'll remember some of the questions in the Cartesian geometry actually use Euclidean geometry, because you might have had a rectangle and then you had to prove diagonals bisect and you found the midpoint and things like that. So there is a relationship between the two. Now, the theorems that we're going to look at, most of them you'll know already. I think what we really need to focus on here is the setting out. Okay, how to present the solutions. But let's define a few things first of all. So geometry definition, some notation that we use in geometry, and some of them you'll recognise straight away, some of them you might go, oh really? So the two vertical lines means is parallel to, the upside down T perpendicular to, three horizontal lines congruent, three vertical lines is similar to our triangle with three dots in that formation, therefore. Sometimes this is one people don't realise they can use, and that's when the triangle is in that format, so it's sort of the upside down, and therefore that's a shorthand way of writing because. When you're explaining something, you say, oh, because this. Terminologies, produced. So when we extend a line in our solution, we call it producing the line. And the way we name it is important, because whoever's reading your solution can do it in exactly the same way. So there's xy. If I was to say xy is produced to A, then again the order is important. I'm going from x to y, producing it to A. So A is on the other side of y. Whereas if I wanted to produce the other way, then I would call the line yx. So now, okay, that's the direction I'm going to produce it in. So y to x out to B. Foot is a really unusual term, because foot sort of implies the base or the bottom, but it doesn't necessarily have to be at the bottom of the picture, because we talk about the base of a triangle. Certainly we talk about base angles in an isosceles triangle. We're really talking about the equal angles there, but for some reason we call them the base angles sometimes. But base or bottom. And in this case, B, again, it's not at the bottom of the diagram, but we would call that the foot of the perpendicular. So where the lines meet, we call that the foot of the perpendicular. Collinear, we talked about that one in coordinate geometry, but that's where points are on the same line and concurrent lines go through the same point. A transversal, and we most normally see that terminology in parallel lines, but a transversal is simply a line that cuts two or more other lines. Okay, conventions when we're naming things in geometry. So we always name our angles and our polygons in cyclic order. Now it doesn't matter whether you go clockwise or anti-clockwise, it just has to be in the same order. So that angle there, I could call it ABC. Now, some people mark their angles with the angle symbol out the front. That's probably the most common way of doing it. The other way of doing it is drawing a little, I think they call that a caret, don't they all? But anyway, that little symbol above the actual vertex, so ABC. It's more unusual, but it is another way of marking in an angle. Now, if there is no ambiguity, then I only have to name the vertex. So if I was to say angle B, well then it's clear which angle I'm talking about there, so that's okay. But if we were to have one like a cross, then I couldn't call it angle B, because which one am I talking about? There's one of four angles I might be talking about, and so in that case I would have to name it completely. And again, I think most people just name all three anyway, just to make life easier. There's a quadrilateral. Again, I could call that VPQT, QPVT, QTVP. Lots of combinations there. In fact, there's a question, how many combinations? Anyway. But as long as they're in order. Oh no, it's more than four. Because you can go clockwise and anti-clockwise. When we name parallel lines, we tend to name them in corresponding order. So AB is parallel to CD. So it gets the direction in the same way. I wouldn't say AB is parallel to DC, for instance. Equal lines, well, we hopefully remember this, we just mark them with the same symbol, usually a dash or a couple of dashes. So there's a quadrilateral where opposite sides are equal. And we say, oh, okay, I know PQ is equal to SR, I know PS is equal to QR. Right. So when we're actually constructing our proof, right, we don't just write anything down. Anything I write down has to be one of the following. Now, the first thing might just be given information. They might have given me some information in the problem. They might tell me two things are equal or something like that. So that's fine. If they've given me the information, obviously I can write it down as a fact. However, don't assume things are given to you. And I think one of the classic ones is here, where they might have a shape and you're told two sides of the triangle are equal. Now, you don't state that it's isosceles straight away. You have to prove it's isosceles. They haven't told you it's an isosceles triangle. They've told you two sides are equal. And so you would write down, oh, well, this side equals this side, therefore the triangle is isosceles. Sometimes we construct new lines or points in our solution. So we should write that down and write down exactly how we constructed it. We might have produced a line from AB to C, meeting at another line at D or something like that. So whoever is reading your solution could recreate that construction. A recognised geometrical theorem or assumption. Now, when you write a theorem down, that theorem should be explicitly stated. Now, whether that is in the setting out or whether that is in the reasoning, it should be there somewhere. So, for example, and the one I've got there is the angle sum of a triangle. People have a habit of writing things down like this. Angle A is equal to 180 minus 25 minus 120. That is not correct. Right? That is not what the theorem says. The theorem says the three angles of a triangle add up to 180. It does not say, oh, one of the angles in the triangle is actually 180 minus the other two. That's not the theorem. So that's what I mean by saying you should write it down explicitly. What the theorem says. The theorem says these three add together to give 180. And then my reasoning is angle sum of a triangle. Now, I've also written equals 180 here. I probably didn't need to because I've explicitly stated it over here. But it needs to be somewhere. Reasoning should always be clear, concise. The last thing that you can write down, of course, is anything that logically follows from previous lines. You might say, oh, A equals B, and then another line you might say, oh, B equals C. Well, then it logically follows, therefore, that A equals C. You can write that down. But that's it. We don't just make up things, which often we see in geometrical proofs. So to start off with, let's look at the angle theorems. And, well, there's a typical sort of situation. We've got two angles on a straight line. We know the angles in a straight line add up to 180. So if I was going to solve this problem, now make sure you read the question. And make sure it is a question where they want working out and all that. Because obviously that's a very quick question. But if it was, I wouldn't just write down x equals whatever the answer is. I'm writing down the theorem that I'm using. And the theorem that I'm using is that the two angles will add up to be 180. Now, there's all sorts of reasoning I've seen for this. I use straight angle. I just simply say, oh, look, we're talking about a straight angle. Because straight angles are 180 degrees. Some people write down, well, what are some of the other things people have written for straight angle? Angle sum of a straight line, angles on a line. Adjacent.
Darn it.
Okay. The thing I hate is supplementary angles. And here is why. What are supplementary angles? Right, so think about what you're saying. This plus this equals 180. Reason, they add up to 180. So if you're saying your reason for them adding up to 180 is they're supplementary angles, you're saying, oh, they add up to 180 because they add up to 180. Therefore, that's true. That's okay. You could say straight angles on the straight line are supplementary. Because now you're giving me more than just saying they add up to 180. You're telling me why they add up to 180. Okay? Better finish off the problem, of course. X turns out to be 150 for those who were getting a bit worried about what the answer was. Vertically opposite angles we know are equal. So if I was doing this one, 3x equals 39. Vertically opposite angles are equal. Yes, they are vertically opposite angles. They're not vert-op. They're vertically opposite. Vert, I believe, is French for green. So if you're talking about the green angles, okay, you can write they're vert angles. X is 13. Angles about a point equals 360 degrees. Again, rather than saying angles about a point, it's a revolution angle. Revolution angles are 360, and so that's what I use. I say, oh, well, they add together to get 360, so we're talking about a revolution angle. Okay, let's talk about the parallel line theorems. Alternate angles, so they form a Z, if you like, if you were just to draw those angles and no other angles. So we say alternate angles are equal, but then we also mentioned the fact that the lines are parallel. Because you can have alternate angles on lines that aren't parallel. They're just not equal. D and E are also alternates. Why are they called alternate angles, by the way? Because which, sorry?
Because they alternate on different sides of the line.
Thank you. Because they alternate on different sides of the lines. Corresponding form an F if you look at them. They're also equal, but there's actually 4 pairs of corresponding angles. Why are they called corresponding? What does corresponding mean in geometry? Say what? Say it again.
It shifts.
That's not what you said.
I said it's the same and the same.
It's the same and the same, okay. No, that's not what I thought you said. Corresponding means in the same position. In the same position. That is why, you know, when you're dealing with congruent triangles, and I know we often use the word matching, but sometimes you see people say corresponding angles in congruent triangles. Corresponding means in the same position. In the same position. Co-interior means
inside.
Co-interior, together on the inside. They, of course, are supplementary or equals 180. Let's look at this problem. We're going to find x, we're going to find y. So I'm going to find x first, it's probably the easiest. So again, as I was saying, I would write down x plus 65 is 180. Because that's what the theorem that I'm using says. These two angles will add together to give 180. So reason? Well, I'm talking about a straight angle. I name the angle, CQD, and I'm telling you, well, that's equal to 180. So x is 115. Now I've got to work out y. To do that, I'm going to construct a third parallel line. I'm going to construct xy such that it's parallel to CD, and it'll pass through the point P. So there it is. Now angle XPQ will equal 65. Alternate angles, and the parallel lines I'm using are XY and CQ. XPB and the one I've labelled 120 is 180. And so they are co-interior angles. XPB is 65. Now, notice I've said 65 and 120 rather than naming the angle. And I guess that's because in the diagram, only one angle has been labelled with 65 and only one angle has been labelled with 120. If there was another angle there labelled 65, then I wouldn't write XPQ is 65. I'd actually name the angle that it's equal to and then say it's equal to 65. All right, well, it's BPQ I'm interested in, and that's the same as saying the sum of these two. Now, I call that common angle because we're saying it's the same angle. I'm just referring to it in a different way. One, I'm talking about the whole angle BPQ. Another way, I'm talking about, it's the sum of these two angles. So common angle is the reason I wrote down for that one. Substitute in, and there's our answer.